Hey guys, welcome to day 47, I think. I'm actually doing my Haskell homework. Well, kind of, not really. I'm just learning Haskell right now because I have a Haskell assignment that's really important and really difficult, and I don't really know much Haskell. I'm practicing Haskell right now using this series. So shout out to this guy, Philip. And I don't know if I have time to code later today, so I just want to record myself coding so I can count the day. Project slightly on hold. I'll probably do some tomorrow. Probably implement the delete feature tomorrow, but other than that, today is a quick Haskell day. But yeah, so I'm doing this exercise right here, which is to create a function nub that removes all duplicates from a given list. And I thought I had it here, but no. I'm like using the one function. Also, hopefully there's no such thing as called nub. I'm using the function here that I also created from exercise 1. And I got it first try, so kind of happy with that. X. Here's the thing, I'm not getting it. It's not working. Yeah. It's just returning me an empty list. Well, okay, I just realized this is a dumb expression because X will always be an A because I'm literally pulling from A. Okay, so maybe I need to do some kind of scene thing, but if you haven't seen it anywhere, well, what if I want to alter this array so I can get how do I get the list in Haskell with without get the list in Haskell without specified I'm not thinking this right. I have create a function that removes all duplicates in a given list. I was trying to use, I don't know if I could use this. I know I'm gonna use list comprehension because that makes the most sense. So if I just do this, it just copies the list, right? That's the first step done, right? Load the Haskell exercise, and then nub b. Right, it's just gonna give me. Oh wait, I can't do that. I gotta do numbers. 1, 2, 3. Oops. It just copies the list, right? That's completely fine. Exercise number. But I need a filter. I feel like I want a guard clause right here. A guard. What values am I allowed to put? Values that I've only seen once. I have an idea. What if I apply lm equals false or some boolean, but value x and xs where where xs equals a crap, I don't know how to do this. This is hard. I know I can do this. lm, I don't know if it's okay, how can I do this? Maybe it's not list comprehension is the best part. Oh yeah, I'm building the list as I go. What about this? As I'm building, put the values of x that for every element in A that are not in X or that are not in. How can I refer to this? X equals or lm x well, this is gonna be always true, right? And this is just literally gonna just give me the same thing because this is always gonna return true every single time. But when it's false or when it's return, place it when you're not in the list. I wish you could freaking not add it in the A. I have an idea. Instead of list comprehension, let's do a recursive list building. So where where the nub is null, just return null, right? Then we want nub A. Okay, let's say A for generic, or let's say xs, right? Ooh, right? Recursively, if x x concatenated with x concatenated with xs nub no, not place x. How can I put a condition? right? Nub is, well, nub is false, or if it's empty, then just return the empty list. If you have elements, take the head and take the remaining elements. Then what do? I want to check. Basically, yeah, I want to do x. I want to do like lm x xs, and then apply x. If that is true, or if it's false, right? Then add it. But how do where can I put this expression? Right, where do I put this freaking expression? Come on. Guard clauses. I would do guard clauses. I could do. I could do this, right? Where we could say the expression I was talking about, lm x xs equals x. I don't know, I can't do this one. This one's hard.
Nub that removes all duplicates from a given list. It's important that it's irrelevant in what order you remove duplicates.
That's close. Okay, if the element xs. I was close, man. Yeah. Okay. Xs equals, then keep going. Nub xs. Right? Okay, so if this is true, then keep going. If it's false, wait, what? Oh yeah, otherwise, oh yeah, skip, otherwise add it, concatenate with that. Yes, that would have worked. I had the idea, I had the logic, but man, Haskell is hard. Comp, what is it? Exercise. Wait, how do I do this? Oh, okay, these are not real things. They're just like pretty stuff. What do you mean? Huh? Oh. There you go. When I reach down. Okay, now nub, so we have 1, 2, 1, 2, 3, 1. I could do guard clauses. So guard clause doesn't have any equal statements.
Of course, if we have an empty list, then we return an empty list since there are no duplicates in it. And if we have some element x in the list, we check if it's an element in XS already. So then in this case, we would have a duplicate and we simply don't add it to our recursive call. Otherwise, we build a new list, x and x prepended to the recursive result. this is the infix syntax for the elem function. You could write it elem xxs and it would be the same. Okay.
Create a function is ascending and returns true if list is giving to it is a list of ascending. Okay, I think that one's pretty straightforward. So the so create a ascending. So is ascending takes in a list of integers, and integers are comparable. They're in the order type class, I believe, of Boolean. Taking a list of integers. So is ascending. So if the list is false or true, maybe true because we made it to the end of the list. Is ascending. We have x s right. Then we can do this. Let's break this down. So we need to check how do we check if it's ascending? All we need to do is basically it's kind of like this, but like an and. Like all of them have to be true for it to be true, as one of them is false. So yeah, I can just do that where x is, oh, who am I comparing to? Greater than xs, and so and is ascending is xs, right? So what I'm saying is x is smaller than xs, right? Well, that's not a good, I can't compare the two. I can't compare the two. Or what if I say like this? I want to solve this myself. I know I can do it. I think this is bad logic. Okay. If we've made it to the end of the list, right? Then it should be true. We've made it to the end of the list, right? But I don't think there's such thing as an early return, so I can't really say for sure. Well, it's okay to say true at the end, but it's just that at a certain position or point, okay, what do I use with the head and tail? I have the use for the head, but I don't know what to do with the head, right? Is ascending. Since true if a list given to it is a list of ascending order. So create a function is ascending that returns true if a list given to it is a list of ascending order. True if a list is given to it is a functional, man, is so hard. So I take an integer of a list of integers. If you're empty, you're good. if you're ascending, okay, if you have elements in the list, what can I do? What can I do? How do I do this? Create a function is ascending that returns true if list giving to it. Let me see the other patterns. So we have like conditionals here, like we can apply continue. If x is less than, I can't compare a list. Like I was doing this, like x is less than xs, and I'm comparing a value and a, otherwise, goodness is prepending it. Right. How do I get the first two values?
List.
How do I get the first two values? Like the way I can only think about it is, well, all I can do is like this. Like, I can do this essentially, right? Like this. Like I can do that, and then all of them has to be just true, and that's your final result, right? If all the, so like is ascending. X is less than, like this. Oh wait, and then we just pass in XS. Okay, so if it's empty list, it's true. So okay, X, then this is hanging, and then I have to go here. X. This is probably gonna break. Yeah, that's not possible. Exactly, it's not. Like this isn't returning. Is it strictly is ascending? So like it has to be, every number has to be bigger than the other. Maybe get, like what's the I feel like there was more stuff to this. Right, we have is ascending equals true. What if theirs is ascending is one list, then return X. Oh, does that violate this? Ooh. Let's see if that works. Bad. Okay, what does he say?
So let's look at a solution.
Okay. Oh, no. I meant true. True. Oh, what? You could do that? X, Y, XS? Oh, wait. Oh. Ah, you can iterate recursively all the time. Okay. That's what I wanted to do. So you could get the first two. You could say X. Wait, what did he do? Okay, so he said X. Okay. Oh my God, you could do that. Okay, X, Y. Right, we're saying X is less than equal to Y, and the remaining stuff is also true. That's what I wanted to do. Because there could be a case where there's not enough. Oh wow, that's really interesting.
This can be done with 3 patterns, and those 3 patterns maybe look a bit weird because we haven't explicitly talked about the third pattern. Let's look at the first 2. Well, if there are no elements in the list, or if there's 1 element in the list has to be of ascending order. But now we have this other pattern that
Wait, that's not true. This is false. Okay, that's weird. Why is this true? That shouldn't be true. It's not strictly ascending. Oh, shoot. Oh, okay. This is what I did. I just passed in. All I'm doing is comparing the first 2 elements. He's breaking it down by saying from Y to XS. Every single value. Okay. Yeah.
we haven't, again, explicitly talked about. So what is this? Well, patterns and pattern matchings can be of a finitely recursive manner. Let's call it that. So you can do a pattern like X, XS, but you can do that same pattern on XS again. So instead of writing X, XS, we can do X, Y, XS. So what we have here is a list that has at least 2 elements in it, and then, some other list. Okay, so let's look at what we're doing here. We look at the first 2 elements of a list, and then see if they are in an ascending order. If that is true, then we look at the recursive result of y-axis, because we cannot look at the recursive result of access, since we have to look at y and the next element in access. This function also could have been done with tail and head and some checking with null, but it's a bit more complicated. This pattern makes it much easier. For the last exercise, we want to look at directed graphs. Those directed graphs are encoded as a list of int tuples. So, for example, we have a list with the tuple 1, 2 in it. This means that we have the nodes 1 and 2, and we have a directed edge going from 1 to 2. Now, for this exercise, we implicitly think of a graph that has all the nodes in it that exist, so you never have to check if a certain node exists or not. Also for this exercise, we're interested in paths. So we are interested, for example, does there exist a path going from 1 to 3? In this case, yes, it does. And does there exist a path going from 4 to 2? Well, yes, it does. But there is no path going from 4 to 1, since the only edge connecting 1 and 2 has the wrong direction. So, okay. The exercise is the following. Create a function hasPath that...
Oh my goodness. This guy he's giving us the hard stuff already. HasPath takes a tuple of ints and ints that takes in two parameters of two integers and returns a boolean. Okay, so it's gonna be like hasPath 1, 2, which returns like true, like that's would be the output. Okay.
That determines if a path from one node to another exists within a directed graph.
Creates a function.
The function, as its first argument, gets a list of the edges, then the start.
Create a function hasPath that determines if a path from one node to another exists in... Damn, bro, that's hard as hell. I don't even know if I could do this in normal code or some imperative programming. Well, that would be a little easier, I think. Okay, so I have a list of tuples that have an integer to integer, so I have to traverse through
starting node, then the end node, and it should return true if there is a path and false if there isn't. Again, you do not have to check if a node is within this list of edges or not. We just implicitly think about it in a way where we say, well, every node that we look at also exists. Okay.
Whoa. Okay, I'm gonna try this. 4 to 1. Okay.
That exist, so you never have to check if a certain node exists or not. Also for this exercise, we're interested in paths. So we are interested, for example, does there exist a path going from 1 to 3? In this case, yes, it does.
1 to 3. Okay, I think I got it. That's hard. I can do it recursively to like check if one matches. Wait, what?
And does there exist a path going from 4 to 2? Well, yes, it does.
But, oh, well, okay. It's just saying, given the two integers, like hasPath. 4 to 1. 1 to 3. Oh, wait, that's true. It's saying
graph that
1 to
has
3 is
all the
valid.
nodes in it that exist. So you never have to check if a certain node exists or not. Also for this exercise, we're interested in paths. So we are interested, for example, does
Yeah.
there exist a path
So like, can I get to 1 to 3?
going from 1 to 3? In this case, yes, it does. And does there exist a path going from 4 to 2? Well, yes, it does. But there is no path going from 4 to 1, since the only edge connecting 1 and 2 has the wrong direction. So, okay. The exercise is the following. Create a function hasPath that determines if a path from one node to another exists within a directed graph. The function, as its first argument, gets a list of the edges, then the starting node, then the end node, and it should return true if there is a path and false if there isn't. Again, you do not have to check if a node is within this list of edges or not. We just implicitly think about it in a way where we say, well, every node that we look at also exists. Okay, so pause the video. The only edge connecting 1 and 2 has the wrong direction.
So 1 to 3, interesting. 2 to 3. 1 to 3, 2 to 3. Okay, so 1 to 3 is valid path because you can get to there. Oh my god. This is hard. Okay, bro.
The general idea of this solution is the following. Exists. Okay, so pause the video now. Okay, so let's look at the solution. The general idea of this solution is the following. We start at the starting node. We then take all the edges that we can. So we look at all the reachable nodes from this one node. We delete all of the edges that we just looked at. This is done in order to not have infinite recursion if there are loops within the graph.
Oh god. Okay, so this is saying if we have an empty list. Oh wait, this is taking 3. Oh, okay. Takes 3, so we have that, x, y. If this is empty, return if these two are empty. Are equal. If it has an element, to some guards. If they're equal, then return true. Otherwise, let xs equal the for every node map in the xs where n does not equal x in or what
graph. And after we did that, we start a new search from every reachable node that we looked at. So let's look at how this is done in the implementation. The first pattern is very simple. If we have no edges anymore to look at, we just have to check if the starting node is the end node. The same goes for the case where we have edges, because in this case, we want to look at, well, is the starting node already the end node? In this case, yes, there exists a path. And otherwise, we do this recursive search. First, we prepare a new list of edges called xs prime. And xs prime is defined as the following. It's all the tuples from xs where n does not equal x. So what are we doing here? Well, again, we are looking at all the reachable nodes going from x. So we have to delete all of the edges we just took. Again, we do this so that if there are any cycles in the graph, this wouldn't be a problem. Okay, then we create a new list out of all the recursive calls to hasPath on this new list xs prime. with a new starting node. And the starting node is determined by the same tuples that we just removed. The tuples were n equals x. So those are the edges where we start at x and then end up at a certain other node. We call this node m, and we start a new recursive search here. Now, if any of these searches returns true, then we found a path. So we OR the whole list, because this would be a list of booleans. So we OR the whole list. We do a logical OR on this whole list, so that if any of these searches returns true, we return
Or the, oh my god, that was insane.
true in the end. Now, there are other solutions for this function. There are actually many solutions. This may be...
Okay, I think that is good for today's video. I apologize for not focusing on the project, but I got a lot of homework to do. But anyways, thanks for watching. I'll see you for tomorrow's video. Yeah, I'll see you.